Hello, my name is Furkan Soysal and I will present our study with Zafer Çıplak titled Photothermal Properties of Graphene Oxide Silver Polyaniline Ternary Nanocomposite. The outline is a brief information about photothermal therapy, aim of this study, synthesis and characterization of the nanocomposite and its photothermal properties, and finally conclusion. Traditional cancer therapy methods such as surgery, radiotherapy, and chemotherapy are highly invasive methods. A new approach, photothermal therapy, is based on photosensitizing agents that generate heat from light absorption. And by this, photoablation of the cancer cells via oxidative stress and mitochondrial depolarization takes place at between 41 and 48 degrees Celsius. So in order to apply high heat deposition and low laser light intensity, we can use near infrared irradiation. Its wavelength is in between 650 and 950 nanometers, and in this wavelength there are low light absorption by tissues, and this minimizes the damage in the surrounding healthy cells. So what we need is a laser illuminator and a photosensitizing agent at the tumor site. So photosensitizing agents should have good dispersibility, high absorption in the near infrared range, high photostability, low cytotoxicity to living system, and selective uptake in cancerous cells in tumors or normal cells in healthy tissues. For this purpose, a variety of materials were studied, including metallic nanoparticles, organic nanoparticles, and carbon-based nanoparticles like carbon nanotubes and graphene. In this study, we selected graphene for this purpose, and its most available form of graphene oxide, which is obtained by oxidizing graphite. It has adequate dispersibility, high loading capacity, and adequate photothermal capacity. So the aim of this study is to develop a photosensitizing agent with high heat deposition, and for this purpose we used graphene oxide for its two-dimensional structure with high loading capacity, and silver for oxidizing aniline, and also silver nanoparticles are antibacterial and non-cytotoxic. And finally we used polyaniline for mainly its strong near-infrared absorption at 808 nanometers, and also its non-cytotoxic under concentrations of 0.1 milligrams per milliliters. The materials we used for the synthesis process were graphite oxide, silver nitrate, aniline, dodecyl-benzene sulfonic acid for acidic medium for polymerization, and phenylendiamine for increasing the rate of polymerization process. And the synthesis method is a one-pot preparation with simultaneous formation of silver nanoparticles and polymerization. Silver nitrate is oxidizing the aniline monomer, and silver nanoparticles in turn reduced by aniline polymerization. So in the synthesis we first took graphite oxide into deionized water and sonicated to obtain graphene oxide, and mixed it with the aniline monomer. After that we added phenylendiamine solution and finally silver nitrate solution, and stirred the mixture for 24 hours at room temperature to obtain graphene oxide silver polyaniline. The role of phenylendiamine in the polymerization of aniline is very important for the chain elongation process. The Phenylendiamine changes the formation of initiation centers and increases their numbers, and in this way the polymerization rate can reach much higher levels. Characterization of our ternary nanocomposite. This one is UV visible spectra of the nanocomposite at various concentrations. This is a typical UV visible spectra of polyaniline, including benzenoid, protonation absorption, and polaron absorption bands. Also, the concentration and absorbance at 808 nanometers is highly linear, which indicates good dispersion stability. The FTIR results of graphene oxide and graphene oxide silver polyaniline nanocomposite shows the typical FTIR spectra of these materials, and X-ray diffraction pattern of graphene oxide shows the typical sharp peak at around 10, and our ternary nanocomposite reveals a broad band corresponding to polyaniline and also a crystalline peak at around 25 degrees. Also, it's shown that silver nanoparticles are formed, and all of silver's typical diffraction patterns are seen in this figure. Scanning electron microscopy results of graphene oxide show its wrinkled two-dimensional structure, and it can be seen in the nanocomposite, also with silver nanoparticles embedded in PANI coating. To determine the photothermal performance of our nanocomposite, we used a laser diode at the wavelength of 808 nanometers. Irradiation times were 10 minutes in all samples, and laser power density ranging between 1.5 and 2.5 watts per square centimeters. We used a lens to focus the laser beam into the dispersion of our nanocomposite, and for the monitoring of temperature we used a thermal camera. These are the heating curves of all concentrations of our nanocomposites, dispersion and water. As you can see, the temperature difference of water is 2.13 and 5 degrees Celsius at these corresponding laser power densities, but the temperature of the dispersion of our nanocomposite reached up to almost 45 degrees Celsius even at the lowest concentration and laser power density, which is sufficient for hyperthermia conditions, and at the highest concentration and laser power density we obtained a maximum temperature difference of 55.7 degrees Celsius. To calculate photothermal conversion efficiency, we use this equation. The only thing we don't know in this equation is heat transfer coefficient. To find heat transfer coefficient, we use time constant method, which uses the cooling period data with dimensionless temperature. So the slope of time versus minus natural logarithm of theta plot during the cooling period gives the time constant, and from time constant we can calculate the heat transfer coefficient. This figure is the heating and cooling curve of 0.1 milligrams per milliliter graphene oxide silver polyaniline dispersion at 1.5 watts per square centimeters, and from the cooling data we plotted time versus minus natural logarithm of theta to calculate photothermal conversion efficiency as 28.7%. In conclusion, our nanocomposite was synthesized by a one-pot technique, and photothermal performance of our ternary nanocomposite is excellent in aqueous dispersions, and we obtained hyperthermia conditions even at the lowest concentration laser power density conditions, and we have a good photothermal conversion efficiency value. The graphene oxide silver polyaniline nanocomposite is a promising photosensitizing agent with its facile fabrication technique, dispersion stability, and photothermal performance. These are our references. Thank you for listening.